Okay, students, here we go again. Now we are starting on the last video, Chapter 10. In Chapter 10, problems are page 348 through 351. Okay. 348 through 351. Okay? All right, so let's look at some problems here. Let's look at number 2 on page 348. It says the two ropes seen in figure P10.2 are used to lower a 255 kilogram piano exactly 5 meters from a second story window to the ground. How much work is done by each of the three forces? All right, so we got a piano and it's being lowered to the ground. All right, and the distance to the ground is 5 meters. Okay, so from here to here is 5 meters. That's distance. It's 5 meters, or X, or whatever you want to call it, R or Y. Okay, actually it would be X though. All right, and I'll show you why in a minute. And the mass of the piano is 255 kilograms. All right. Let's look at the three forces. So we got a force here. Let me move this over. So the mass of the piano is 255 kilograms. So we got a force there. It's 1,830 newtons. Okay, and the angle with the surface here, this angle is 60 degrees. And that's, they call that tension 1, T1, which is a force. All right, T2, this angle is 45 degrees. And that's a force of 1,295 newtons. And then T3, which is the weight of the piano, is 2,500 newtons. Okay, we won't say T, we'll just say weight. It's 2,500 newtons. Okay, now don't forget that tension and weight and normal forces, those are all forces, just different types of forces. Okay, so what do we need to do? First of all, we need to define where our X and Y axes are, especially on this one. All right, now since the piano is going down, we're going to put X in this direction. We're going to tilt the axis, and Y is in that direction, okay? We're going to flip everything around, okay? In other words, we're going to make X straight up and down and Y horizontal, okay? And you say, can you do that? Sure you can. Because if you remember how we define work, work is when a force is applied to an object through a distance, and it causes that object to move through a distance, and that distance will be in the X direction. So it's all dependent on, you say, how do you know which way to establish that? It's all dependent on the direction that the object is moving, and the object is moving down. So therefore the force applied, which is weight, is causing the piano to move downward. So our X, positive X, is towards the ground. Actually the work is being done by gravity, okay? The work done by gravity is positive. Why? Because it's moving in the direction that gravity is pulling it, okay? It's moving in the positive X direction. So that's how we define it. So if you remember from our lectures, if you watch those, work is defined as what? The force times X, the distance it moves through in the X direction, and it's the dot product, by the way, if you want to get into some calculus. It's actually the dot product or the scalar product. Work is a scalar quantity. It's not a vector quantity, all right? So it's the dot product of the work, the force done through a given distance, okay? So the work done by weight or gravity The force is 2,500 newtons. The distance is 5 meters, and it's cosine of 0 degrees because it's moving in the positive x direction. So the work done by the weight, or we could say the work done by gravity, is what? All right, so we got 2,500 times 5 is 12,500. Now, the cosine of 0 is 1, so it's going to be 12,500 joules, and that's positive, okay? So the work done by gravity is positive, okay? But now what about the work done on T1 and T2? Okay, so the work done on 1, well, let's look at this. It's the same equation, but now we've got to figure out what our angles are. We've got to figure out what our angles are. Well, okay, y'all, from here to here is 90, and from there to there is another 60, so that's a total of what, 150? That's 150, isn't it? Yes, it is. So the work then done is what, 1,830 newtons times, okay, it's still moving now. It's still moving through a distance of 5 meters, but it's at an angle. That rope is at an angle. So it's 5 meters times a cosine of 150 degrees. Well, that's going to be a negative number, isn't it? So the work done on rope 1, T1, is what? So we got 1,830 times 5 times cosine of 150. And what do we get? We get a negative 7,924. So it's a negative 7,924 joules, because a newton times a meter is a joule. We are not talking about torque. Okay? We're not talking about torque. And by the way, you can put these into kilojoules. This would be 12.5 kilojoules, and this one right here would be 7.9 kilojoules if you want to do that. Okay? All right, so there's that one. There's that one. Now let's do the work done on number 2. Same thing. We use the tension, 1,295 newtons times the distance. It's still moving through 5 meters, but we got to find the angle, don't we? Okay, well, look, from here to here is 90, and another 45 added to 90 is what, 135? So it's cosine 135 degrees, which is going to be negative. So the work done on 2 is what? Well, we got 1,295 times 5 times the cosine of, what did I say, 135? And we get a negative, the work is negative 4,578.5. We could just say, go ahead and round it to 79, 4,579 joules, or we could say we could round that to 6, round that up 6 kilojoules, negative, okay? All right? Or leave it 4.58 if you wanted to. It all depends on the number of significant figures, okay? All right. Okay. Okay? All right. So that is that problem. I think that's all of it. Yeah. What's next? Number 15. Okay, so number 15 is on the same page, 348. Okay, and it says Sam's job at the summer amusement park is to slow down and bring to a stop the boats in the log ride. If the boat and its riders have a mass of 1,200 kilograms and the boat drifts at 1.2 meters per second, how much work does Sam do to stop it? Okay, so let's draw it. Now, you know, you really need to draw these problems. So we got a boat here, okay. Actually, it's down in the water, isn't it? We don't have to get that technical, but okay. And we got people in it. There's somebody there and there and there. Close enough, okay. All right, and so the initial velocity of the boat is what? Well, it's drifting at what? 1.2 meters per second, okay? And the mass of the riders, let's see, if a boat and its riders have a mass, so mass total is 1,200 kilograms, right? Okay, so that's everything, boat and people and everything. All right, how much work does Sam do to stop it? Well, when Sam's right here on the deck, so he's standing right here, and so when the boat gets right here, he's got to reach out and stop it, doesn't he? Close enough. Okay, he's headless. He's got to reach out and stop it. So the final velocity of the boat is what? Well, it's 0 meters per second, isn't it? It sure is. The mass hasn't changed. Nothing has changed. So really, what is this? This is change in kinetic energy, isn't it? We know that work, if you watch the video, lecture video, is equal to delta K. And we know that delta K is equal to what? K final minus K initial, isn't it? Well, y'all, K final is 0. So we got to write right here, K final is 0 joules. Orange juice, right? 0 joules. How do you know that? Because there's no velocity. When you plug that in, it's what? 0. Well, we know that kinetic energy is found by 1/2 mv squared, isn't it? It sure is. And by the way, it's a scalar product too, because it's related to work. Work and kinetic energy are related to each other. They're basically the same way, just a little different way about getting to it, okay? All right? Work deals with forces, but kinetic energy deals with velocities, doesn't it? Okay, so we're left with what? Well, then the change in kinetic energy is equal to what? Negative Ki, isn't it? So the change in kinetic energy is equal to 1/2, negative now, 1/2. The mass is 1,200 kilograms times what? The velocity was 1.2 meters per second squared. Did I write my squared? Yeah, I wrote my squared on there. So we square 1.2 times 1,200 times 0.5, and we should get 800. We should get 864 joules, right? And that's what? That's a negative 864 joules, isn't it? Or a negative 0. Oh, shoot. I need a break, okay? Whoops. 864 kilojoules, isn't it? If you want to write it that way. Okay, so it's negative 864 joules. Okay. But now remember, what is this asking? What is this asking? Well, the magnitude would actually be what? Okay. The magnitude of that is actually, the amount that he does is actually 0.86 joules, kilojoules, or 864 joules. So that's the work that the boat does on Sam, right? Think about it, because we're talking about the boat, it hits Sam. We get a negative answer, don't we? Okay, so what does that mean? So that means then the change in kinetic energy, or the amount of energy that Sam does, or K, let's just write it this way. So then K is equal to 864 joules. Now what do you mean? All right, it all depends on how we're looking at it. If we're talking about the change in kinetic energy of the boat, then it's negative 864 joules. But what does that mean? That means that Sam has to do 864 joules of work on the boat to get it to stop. Does that make sense? Because the boat's going this way. So what does Sam have to do? Well, he has to push back this way, doesn't he? Okay, so again, let me say it one more time. The boat does negative 864 joules of work on Sam. Therefore, Sam has to do a positive 864 joules of work on the boat in the opposite direction the boat is going to get it to stop. Does that make sense? I hope it does, okay? All right, let's move on to the next question. Let's look at number 24. All right. And number 24 is on page 349. All right. How far must you stretch a spring with a K constant of 1,000 newtons per meter to store 200 joules of energy? Okay, so I don't care. How are we going to do this? We're going to do it this way. We got a spring. Okay, and so we're going to stretch it that way. And we want to know how far. We want to know x final, don't we? How far will we have to stretch it? Well, the K constant is 1,000 Newton meters, and the amount of energy elastic that is stored in it is 200 joules. Okay, so we want to know how far are we going to have to stretch it. Okay. All right, so we know by definition then that U elastic is equal to 1/2 kx squared, right? And so we want to know, and that's not delta x, that's x. That's the total length. That's how far, okay? So then to find, we're looking for what? We're looking for x, so x is going to look something like this, isn't it? When you solve for x, it's the square root of 2 U elastic over what? K, and that's all under the radical. Okay, does everybody understand that? That all has to be under the radical. Okay, everything has to be under the radical. 2U over K. All right, so you plug it in, and so you got the square root of 200 joules times 1,000 Newton meters divided by, dang it, I'm sorry. Slow down. All right, so that's 2 times 200, I'll get it right eventually, divided by 1,000. There we go, newtons per meter. And so we get an x of what? All right, well, let's work all that out. So we got the square root of 2 times 200 divided by 1,000. And that is not right. Okay, let me do it this way. 2 times 200. There we go. You get 0.63 meters. Okay, 0.63 meters. That's a good problem. And then let's look at one more, number 38. Okay. I love those elastic energy, potential energy problems using springs. Those are good problems. All right. All right, let's look at number 38. Let's look at number 38. Okay, so we've got number 38, and that's on page 349. Yeah. That is the last one, correct? That we're working, yeah. 349, okay. All right, it says you in an emergency start a manual transmission car by putting it in neutral and letting the car roll down a hill to pick up speed, and then putting it in gear and quickly letting out the clutch. If the car needs to be moving at 3.5 meters per second for this to work, how high a hill do you need? Okay, we're going to ignore friction and drag. Okay, so we got a car going down a hill. Okay, car going down a hill, going that way, it's coasting. Of course, we know we got gravity's pulling it that way, don't we? All right, and the car needs to be, so the final velocity needs to be 3.5 meters per second. That means its initial velocity is 0 meters per second, right? Okay. So in order for this to work, we got to get up 3.5 meters per second and then put it in gear and pop the clutch. All right, so how much work? It says how high does the hill need to be? So we need to find H, okay? Question mark. Okay? We need to know how high it is, right? Well, we know from lecture and conservation of energy, we know that the change in potential plus the change in kinetic is equal to 0, right? It is equal to 0. Now, let's look at this. Let's go through this. So we know what change is. We know this is that delta U is equal to U final minus U initial. Actually, it's the other way around. U initial minus U final. Okay. But we'll go ahead and go with that. And we know that delta K is equal to what? K final minus K initial. All right? Because look, if we rewrite this equation right here, watch what happens. Delta K, dang it, delta K is equal to negative delta U, which is correct. Now, what the heck does that mean? Okay, look, y'all. When kinetic energy is getting more positive, potential energy is getting more negative. I'll give you an example, all right? Is there any potential energy when the car's setting still? Yes. So U initial is maximum, isn't it? What is K initial? 0. All right, when the car gets to the bottom of the hill and you pop the clutch, all right, when you get to the very bottom of the hill, and that's supposed to be the bottom, but anyway, I didn't have room to write it, then U final is 0 and K final is maximum, right? Absolutely. So U final's gone and K initial's gone. So really what are we left with? We've got K final is equal to a negative negative. Look, see right here? A negative U initial, which becomes positive. All right? All right. Isn't that neat how that works out? Okay. So we have what? We have 1/2 mv squared is equal to mgh. And so h is equal to 1/2 mv squared over mg, isn't it? Huh. Well, look, you say, Miss Shields, they didn't give us the mass of the car. The mass cancels out. And so h is equal to 1/2 what? Velocity squared divided by g, right? Okay, so let's plug in. So h is equal to 1/2. The velocity is what? 3.5 meters per second squared over 9.8 meters per second squared. And so what do we get? What do we get? All right, well, let's see what we get. 0.5 times, whoops, do it backwards. So 3.5 squared times 0.5 divided by 9.8. All right, and what do we get? We get 0.625 meters, or you could say 0.63 meters. Okay. That's a really good problem. You say, why do you like those kind of problems? Because look, it shows you the relationship between potential and kinetic energy. That when you sum up potential and kinetic energy, you sum them both up, it should equal 0 when we negate friction and drag, okay? So in other words, when we're not looking at any external forces, the sum of potential and kinetic energy should equal 0, okay? Okay. All right, so there's your answer. Okay, I'm going to take a break and get ready for the next chapter. Okay, students, let's start with chapter 11 now. So we're on chapter 11, pages 385 to 387. Okay, so we're going to look at number 1. And it says we got a 10% efficient engine, so the efficiency is 10%. Accelerates a 1,500 kilogram car from rest to 15 meters per second. So we got a car, okay, and it accelerates from initial velocity of 0 meters per second to a final velocity of what? 15 meters per second. All right. How much energy is transferred to the engine by the burning of gasoline? So we want to know how much work is done by the gas, okay? Or how much energy. Work is energy. We could also call this work out, all right? Okay? And the car was what? The mass of the car is 1,500 kilograms. Okay? So it says how much energy is transferred to the engine by the burning of gasoline. Okay, well we need to think a little bit back to our previous chapter when we were lecturing about energy. We know that work or work out is equal to what? The change in kinetic energy, isn't it? It sure is. The work is equal to the change in kinetic energy. Well, we know that kinetic energy initial is 0 joules. So then our equation K final minus K initial, which is equal to, which delta K is equal to, then K initial is gone, and so therefore the work out is equal to the final kinetic energy, right? All right, so this is actually an efficiency problem, isn't it? Well, yes, it is, because we can find the efficiency of an engine is equal to the work we get out, which is the work done by the gasoline out, divided by Q hot. Okay? And Q hot, or the work done out, is the kinetic energy. Q hot is the thermal energy, right? That's the thermal energy. That's how much the gasoline will do. Because you burn gasoline and it's what? It's thermal energy, isn't it? So therefore then Q, which is the same thing as saying work, is equal to what? The work out, which is the kinetic energy, divided by the efficiency. So Q then, which is thermal energy, which is Q of the gas, if you want to write it that way, which is thermal energy. Now, are these related? Is Q equal to work? Well, yes, it is, but you've got to realize what type of Q is it? Is energy being done on the system or done by the system? There's where you have to keep your system straight, okay? So the energy is being done on the system, okay? In other words, the gasoline is doing work on the car, so it has to be positive. So Q has to be positive, okay? And if Q is positive, that means there's heat, there's thermal energy, okay? Okay, so then the work out is 1/2 mv squared over E, and so we got what? 1/2 times what? The mass, which is 1,500 kilograms, times the velocity squared, and the velocity was, where did I write it? 15 meters per second, and then we square that value, divided by, all right, we got to convert 10% to a decimal. We'll divide by 100, that's 0.1. That's the efficiency, okay? You can't put 100% in, you got to convert it back to a decimal. Divide by 100. So then the Q of the gas is equal to what? Well, let's see. We got 15 squared times 1,500 times 0.5 divided by 0.1, and we should get what? We should get a huge number. 101,687,500. So we get 1,687,500 joules, or we could say what? 1.68 times 10 to the what? Times 10 to the 6th joules. We could also say megajoules, or we could just say 1.7 megajoules, okay? Or 1.68, 1.7 times 10 to the 6th, okay? So there's your answer right there, okay? There it is. Hope that makes sense. All right, let's look at another one. Let's look at number 31. Yeah. All right, let's see here. Yeah, number 31. So we got 500 joules of work are done on a system in a process that decreases the system's thermal energy by 200 joules. How much energy is transferred to or from the system as heat? Okay, so we got, this is number 31, and this is on page 386. Oh, God. I wished I could write neater. I know y'all do too. Page 386. I apologize, okay? Okay, well, this is a fairly straightforward problem. So we got a system, and I don't know, let's just, do we have to draw it? Well, let's just do something like this. Let's say like a box, and we got a person here, and they're hitting it with a hammer, okay? Okay, I don't know. All right. So 500, so the person is doing 500 joules of work, okay? Which is being done on the system right there. In a process that decreases the system's thermal energy by 200 joules. So Q goes down by 200 joules, right? It decreases by 200 joules. Okay? Q is thermal energy. That's why we write Q instead of W. Is it still work? Yes, it's just a different form of work. How much energy is transferred to or from the system as heat? Okay. All right, well, we know by definition, again, from our lectures, okay, the change in energy, thermal energy, is equal to the work plus Q, okay? So we're looking for Q, aren't we? Correct? Now, let me make sure I've written everything properly. Yes, I have. So the change in energy, this is not actually Q. I labeled that wrong. I'm sorry. This is actually the change in E. Okay? That's the change in E. We are looking for Q because it says, I should have caught that, how much energy is transferred to or from the system as heat. This is heat. This is work. This is the change in internal energy, okay, or thermal energy, okay, and it tells you that the process decreases the system's thermal energy by 200. So that's when it decreases by that amount, that means that's delta E. My bad. And it is negative 200 because it decreased, okay? So solve for Q. Q is equal to what? Delta E minus work, isn't it? Okay, so Q then is equal to what? Negative 200 minus 700 joules. And we get a what? I'm sorry, not negative 700. That's the answer, crazy head. 500. And we get an answer of negative 700 joules. So that's how much it loses, okay? So it says, let's read it again, how much energy is transferred to or from the system as heat. So it's losing 700 joules. So where is it losing 700 joules? It's going to the environment, okay? So 700 joules of energy are being lost to the environment. It's a pretty big loss, okay? That's a pretty big loss. You're losing a good bit of energy there. That's not, what we would like to see. We'd like to try to conserve as much of that energy. That's why if you've ever noticed, if you ever take a hammer and beat on something, you exert a lot of energy, but you don't get very much work done, do you? That's why you have to hit it a lot. You ever thought about that? Well, that's because a lot of that energy is being lost to the environment, okay, to the surroundings, okay? If you ever think about things like that. All right, let's look at number 36. And it's the same page. Let's see. So we got number 36, and that is page 386, right? Yeah, page 386. All right, it says a heat engine exerts 55 kilojoules from a hot reservoir. So QH is equal to 55 kilojoules. That's 55,000 joules. And exhaust 40 kilojoules into the cold reservoir. Okay. All right, and so the cold reservoir, Q, is equal to what? 40 kilojoules. All right. what are A, the work done, and B, the efficiency? So how much work is done, and what is the efficiency? Okay. All right, so we know then from our lecture that work out is equal to what? QH minus QC. And so we plug it in, don't we? So how much work is done? We've got 55 kilojoules minus 40 kilojoules should equal 15 kilojoules. So we actually get 15 kilojoules. So does everybody see that from the hot reservoir to the cold reservoir, we have a positive work out. And that's what you want. You want work to be positive, okay? You want your work to be positive, okay? It has to be, okay? Well, I say it has to be. If you want to get anything done, it needs to be in most situations, right? Every situation, okay? Now, that's part A. What about part B? Part B says, what is the efficiency? Now, there's a couple of different ways we could work this. We could use our efficiency equation, or we could use our elementary efficiency equation we used a minute ago, or we can use this equation, the efficiency, and this is the equation, I forget what page this is on. Yeah, this is on page 370, equation 1110. There's another way we can compute the engine's efficiency. It's really just by doing some substitution. So we got what? E is equal to 1 minus QC over QH. So 1 minus QC, which is what? 40 kilojoules divided by 55 gives us an answer of what? 0.27 is the efficiency, right? Do your math. So 1 minus 40 over 50. Is that right? Did I do everything right there? Oh, not 50, 55. I'm sorry. Yeah. 0.27. Or we could say its percentage of efficiency is 27%. That's not very efficient, is it? That's not a very efficient engine. Okay, so if you multiply that times 100, it'll be 27% efficiency. Ooh, losing a lot of energy. That's costing some money. All right, then let's look at our last problem, number 45. We have number 45, and we are on page 387. Okay. So number 45 says a refrigerator, so let's draw a refrigerator. There's your handle. Takes in 20 joules of work. Okay, so that's work in. So the work in is 20 joules. Okay. And exhaust 50 joules of heat. So Q is what? 50 joules of heat. Is that right? And that's Q hot. Okay. So it exhausts 50 joules of heat. That's Q hot, right? What is a refrigerator's coefficient of performance, COP? What is its coefficient of performance? So it takes in 20 but exhausts 50. Well, it took in 20, exhausts 50. So that's, and that, notice it said now, you got to watch this, exhausts 50 joules of heat. Well, that's QH. Okay, it's getting rid of it. So according to our lecture in our textbook, COP is equal to QC over work in, QC over work in. Or we could write it this way, QH minus work in, divided by work in. So the COP is equal to QH, which is 50 joules, minus 20 joules, divided by 20 joules, and that's equal to what? Well, you've got 30 divided by 20, which is 1.5. So that's pretty good COP, coefficient of performance, okay? If it's taking in 20 and getting rid of 50, it's basically doing what? That it's getting rid of what? 1.5 times? Did I do that right? 50 minus, yeah. So it's getting rid of 1.5 times more. It's exhausting 1.5 times more, correct? Than it's taking in. No, excuse me. So yeah, so it's taking in 20, it's exhausting 30, so it actually has a net gain of what? It has a net gain of 30 joules, doesn't it? So that's pretty good. That's pretty good. It's getting rid of more than it's taking in, especially more than one time, okay? That's doing pretty good. Okay. Hope this helps.